we can do the same thing with losses. If we know, if somebody in the market tell us what is the average, what is the mean price of this screen, or what is the mean price of this TV? Oh, okay, he will tell me the average prices that the US citizen spent on buying TVs is between $200 and $100 or $1,200. So you have an upper and lower bounds for how much people spend on TVs, okay? So you can sample or make a distribution and then sample a 1,000 sample of the TV price. Same thing here. Like you can see, this is a normal distribution on how much people can spend on like painting their house. Like it's like from $900 to $2,700. And this is a normal distribution that shows how much is the mean and how much is the high cost and the low cost. And we can use this normal distribution to generate a 1,000 sample of the replacement cost of each component. And this includes TV, includes appliances, furniture, drywalls, even like the structural components itself. If you have a roof damage and you want to hire a contractor, so the contractors can charge between an upper and lower bounds, and we can build a normal distribution and sample from this distribution a 1,000 sample of how much this replacing the roof is gonna cost me. And we can put this 1,000 samples in a vector. Okay, like this vector will have, like for example, I'm painting this room, and this is gonna cost me on average $1,700. So I believe I'm gonna find like 1,600, 1,500, 2,000. 2,100, I will have lots of numbers, 1,000 numbers. So right now, I want to find what is the replacement cost of the component if I was hit by a hazard, okay? So I have the probability of damage, like for example, does the replacement cost of this component, or let's talk about the TV. Here, if I have 0.3, what is the replacement cost? So it will be the probability of damage that you will have. So here I will have, for example, probability of damage of 7%. Does it the replacement cost will be the same if I have 1 meter flood depth? No, because the probability that your TV is going to be damaged, it will be much more. But 0.3 meter, maybe the water will not touch the TV. So the probability of damage will be very, very low. But if you have 1 meter, yeah, your TV, the water might get here and you might have a probability of higher damage. So if we want to convert the damage into losses, we need to multiply the probability by dollars. Okay, so right now we have a vector that has the dollar value of the replacement cost of the component, has 1,000 value. So the next step is I multiply the probability of failure of the component by the replacement cost of the component. So this is what is next. So the first equation is the fragility equation that has the number of fails over the total number of samples. And this tells me what is the failure probability of the component. The next step is I multiply the failure probability by this vector that has 1,000 value. So it will tell me finally what is the replacement cost of the component, but it will not tell me an exact value. It will be still a vector. So if I have the probability of failure 0.1, and this vector has the replacement cost, so this one will be 0.1 multiplied by the replacement cost of each value. And I do the same thing for every component in the building. The appliances, the furniture, the flooring, the carpet, the chairs, everything in your building. So you will have, if you want to calculate the total replacement cost or the total damage cost that you have in your building, you will have to sum all the damage of all the components in your building. So you will have a vector for the fridge, for the washer, for the dryer, for the appliances, for the drywall, for the trusses, for the frames. So you will have all the components and you sum them and you will get another vector. This vector will have 1,000 value, but this 1,000 value will be the total replacement cost of your entire building or the total damage for your entire building because we summed all the components. Okay, it will have 1,000 values. So the next step is you want to make a sense of this 1,000 value. So you take a mean. So you will take the mean of all these 1,000 value and the standard deviation, and you will finally end up with having one value, which is the mean replacement cost or the mean damage that happened at flood depths. Like For example, let's say a building hit by 1 meter flood. So you will find what is the replacement cost of each component. If you have like a ceiling, so this one is not gonna be damaged. So the losses for all these stuff will be zero, but this one is gonna be damaged. This screen is gonna be damaged. So you will have vectors that has lots of zero and vectors that has lots of losses. It's these vectors, right?
Mhm.
And as the water goes up, you will have vectors that get filled with losses, right? And then we sum all of them and we get one vector at one flood depth. Okay, this is at only one flood depth, and we keep repeating the same for every flood depth, for 1 meter, 1.5 meter, 1.2 meter, until we make a curve for how is the losses is getting increased with the amount of flood depths. So we have done this for the component, and this is how we do it for the entire building by summing all the components. All right, so, and we did this. This is an example of one-story residential building on a crowded space foundation, and we divided this building into all the components that has like 65 components. And this is the fragility curve for each component. Okay, like 65 fragility curve. And as you can see, the first, like here at 1 meter, we have most of the fragilities of the appliances. Here, like fridge, stove, washer, dryer, so we'll have lots of fragility at 1 meter, because at 1 meter, you have almost all the component in your apartment, like tables, furniture, most of the appliances, most of the gadgets, lots of things. But here, you'll start to have damage, to see damage to the drywalls, and then you will see damage to the like the walls, the framing, the ceiling, the roof shingles, and all the damage for the other component. The second step is to convert this damage to losses, right? And this is when I told you, we multiply the probability by the replacement cost. So this curve is the same as these curves, but this is actually for just 6 components. I didn't make it for all the components that we have here. So this is just for 5 components. And what I did, I multiplied the probability of failure at each flood depth by the replacement cost of the component. So we finally convert the damage, percentage damage, to losses in dollar value. So this is how much dollar value that I'm gonna lose, because we multiplied by a vector that has dollars. And the gray area is the standard deviation in the losses. Because if you remember from last slide, we had a 1,000 value. So we got the mean and a standard deviation. So this value, this curve is the mean, and this range is the standard deviation, and the standard deviation is plus and minus. So it could be plus or minus. Okay, and then we were able to make a building fragility functions. This building fragility functions, as we told you last time, we put the components in a groups. And we say if this group is damaged, so damage state 1 is exceeded, which is a slide damage. If group 2 of components damaged, so damage state 2 is exceeded. And that's what we do here, like damage state 0. So if you have a flood depth of like 0.25 meter, so damage state 0 is like, so you will not have damage state 1 or 2 or 3 or 5, because the water is just like here, very low. It doesn't cause that slide damage state, maybe like insignificant damage. But if the water is here, like 1 meter, so damage state 1 will be exceeded, like it will be 60%, but damage state 2, it will be very low. And then as the flood depths get increased, the probability of exceeding more higher damage state will be much more. Like for example, if a building is submerged with water like 7 meter flood depth, so damage state 4 is 100%. Like your building will be completely damaged 100%. Okay? And the second thing is to convert the building damage, the building fragilities, into loss functions. And that's actually what we did here. Like here, at each flood depth, like let's assume X is flood depth 1 meter. Okay. So what we did here, we found how much losses I will have at 1 meter flood depth, but I found them in a 1,000 value. So this curve, each single point, if I take a vertical line, you will hit a 1,000 point of the replacement cost at flood depths of 1 meter. Okay, so let's go back. So if let's assume here there's a 1,000 value at flood depths equal to 1 meter. So this points, if at 1 meter I make a vertical line, I will hit 1,000 of these small points. If you take the mean, it will be the black line in the middle. If you take the standard deviation, it will be this shaded area. And at each flood depth, I did the same, 1,000 value. And also at 3 meter, you will find 1,000 points. But we care about the mean and one standard deviation, so we can have some idea how much losses that it will have. Okay. Okay, so this how we moved from component level fragility curves to component level loss curves, and from building level fragility curves to building level loss curves. And actually, we can do this at
A question on the previous slide. Yeah. But what the simplification seems to be starting at some point and increasing.
Oh, you mean it's not the same?
Yeah,
because
here and the other part.
It depends on the uncertainties in the components. Like some components maybe here have less uncertainties than the components here.
Yeah, but for example, the other curve, the above curve.
This one?
For an exact component.
Yeah.
It also shows.
Because let me tell you, here the standard deviation is less because the component is getting damaged. But once it hit 100% damage, so it's already damaged. So you know that this component is already damaged. So this is how the uncertainty is coming from. But also another source of uncertainty is in the price itself. So the price of the component also is uncertain. So it's a double uncertainty. So this is actually, I believe, how the uncertainties get varies. Like here, I might also you might check because you don't know which one affects more. Is it the uncertainty in the elevation of the component or the uncertainty in the price of the component?
Because I took from the previous slide.
Fragility when it's not curved anymore. It will be a surface. Like if you include the uncertainty in the damage of the TV from flood depths and also flood duration, or any component from flood depths or flood duration. For example, even for wind, you might include wind speed and you might include other parameters, maybe debris damage, like how much you will have if the debris volume is this and the wind speed is this. Or wind rainfall intrusion, how much rainfall that you got inside your building and also how much was the wind speed. So the fragility will not be a curve anymore. It will be a surface. And this surface, you will have to enter by two values. For example, this surface tells you what amount of losses you will have at flood depths and also flood duration. This can be also a flood velocity. So, and intuitively, if the flood depth is getting higher, the flood losses is going to get higher. And if the flood duration is getting higher, so also the flood losses is going to get higher. Okay, so the surface will be going this way. Same thing with this is a lost surface. Same thing with a fragility. As soon as the flood duration is getting higher, the exceedance probability of a damaged state is getting increased, and also the flood depth, if it's getting higher, it's also getting increased. Okay, so we applied this concept for a portfolio of building archetypes, like 15 building archetypes, that one that we talked about them yesterday. And this is actually some of the BIM models for these archetypes. This one is a 2-story residential building on a crowd space foundation. This is a multi-family residential building on a slab brick foundation. We have gas station, shopping center like Walmart. It has every component in Walmart, like all the fridges, all the aisles, everything that you can imagine. And everything on the shelves and everything in the fridges. So all this is included. Strip malls with different sizes, office buildings, school, 1-story and 2-story school, hospital, community center, and lots of other archetypes. So we applied the same approach and we get a fragility functions for all of them. Like here, it shows you the loss curve for each one of these archetypes from 1 to 5. For each archetype, knowing the flood depths, you will know how much damage that each archetype or each building will have. Then the next step is to shift this analysis from the building level to the community level. So all what we did right now is just component level analysis and building level analysis, but we didn't know how to do community level analysis. So for community level analysis, first, we will need the hazards so that we can know the hazard intensity at each building. And then we need to know where are these buildings. So we need a shape file or a GIS file that tells us where the buildings are. and then we overlay them together, and we know, and we do some spatial analysis, and we know the hazard intensity at each building. And then we use this hazard intensity in an algorithm that tells us what is the damage for each building. But we need to know what is the building type, because each building has different damage curve, right? So we cannot use one damage curve for all the buildings. So first, we need to do the archetypes assignment. You guys remember from last time that we developed the mapping algorithm that can map these archetypes to every building based on the building information, like the number of story, the occupancy, the foundation type, and all the information about the building, right? So we know what are the building types, and based on this, we assign vulnerability functions for each building. Then the next step is the challenging one, is to build an algorithm that assign these archetypes or assign these fragilities for each archetype, and then do building by building analysis like a for loop and say, check the hazard intensity at each building and go building by building and run the fragility and identify the damage corresponding to flood depths to each building. So what does the algorithm do? It makes a for loop, like goes building one, check flood depths, check the fragility, enter the fragility with the flood depths, calculate damage, put the damage. And is it done? Go to building number 2, and you keep run this loop until you finish all the exposed building. So that's what the flow chart for this algorithm do, like for buildings from I1 to N, and then calculate damage state 0, 1, 2, 3, and 4, and then calculate losses. And then if you get the losses, you increase I, and then you go back to building number 2, building number 3, until you finish all the buildings. And then you get a new shapefile or a new GIS file of the community that has another column that tells you what this building, how much losses that this building is going to have. And then you can present this, like here, it shows shows a color-coded map for actually a real community that we investigated, with buildings color-coded based on their damage state. Like the building that has blue is not damaged. The building that has this color has damage state 1, slight damage. Building that has orange, they have damage state 2, moderate damage. 3 means like extensive damage, okay? So this is how we shift the process from building to the community level. Does anyone have any question? All right, so the next step is the mitigation analysis. So we can take advantage of the method that we developed because it's at the component level, and we were able to shift it from component to building and from building to the community. So we can investigate a wide different types of mitigation measures. Like, for example, if you think about it, okay, I'm gonna hit with a flood. So how about if I take this TV off and put it in the second floor? How about if my appliances, I put them on a table or I put them on a blocks? What if I will take all my electronics, computers, laptops? So once you shift the elevation of this TV to another elevation, the fragility will be completely different. The fragility will be pushed away, so you will need much more flood depths to damage this component, right? So we can investigate this. Elevating the building from the ground, this also can be investigated. So let's see what kind of mitigation measures that we have. So here, it shows you how, for example, how can you see the first floor? It's empty, right? Somebody knows that there's a flood is gonna hit, so he moved all the component up there. And if component that doesn't fit the stairs, he put some blocks. And also he put sandbags. So he's doing everything that he can to survive as much component as he can, right? So yeah, it's a good thing, but how can we measure how much loss reduction that this guy gonna have? Is it worth the effort or not? So this is also a good thing, because sometimes you can risk your life. You might you have 3 hours to be flooded and you need to get out of your home. So is it good that you risk your life for a couple $1,000, or you risk your life for 10 or 20, or is it not risk your life? It's just you're gonna hit was 2 feet or 3 feet of water, so you just make as much component to survive as much as you can. Because also this is gonna help you to recover fast. Because if you have less losses, so you will have to spend less when you recover. You will only pay for changing the drywalls or changing the carpet. So it's less expenses in the recovery. This is very important. Okay, so I'm gonna show you how we develop a big algorithm that can investigate all the possible mitigation measures. So this is actually a flow chart of how we can investigate the mitigation. So this flow chart is actually was expanded to a 6,000 line of coding. So let's see what this flow chart is doing. So this flow chart actually read the flood depth resistance of the component and the flood duration resistance of all the component in the building. And what is the component's replacement cost? So all these are inputs. The component's replacement cost, the resistance of the component and everything. And also the mitigations. If somebody's gonna use sandbags, if somebody's gonna use seal doors, flood resistance walls. So we need to know what is the mitigation measures that are in place. And then the second thing, if you are going to use a flood barrier, some people have what is called bladder dam. Bladder dam is something that you blow up and fill it with water and doesn't allow the water to get in your building. Actually, I have some pictures here. So this is a bladder dam around Walmart building. And you can see you have like 3 feet of water and the water didn't make it inside. Also, yeah, something like this. So this is called a bladder dam. So I have to input this in my model. And then I will run and see how much loss reduction I will have if I use this. But I have to make the flood depths variable so that I can capture this. Because if you have a bladder dam of 1 meter height, but what if you got 2 meter high flood depths? So all the effort that you did will be gone because it will be overflow and everything will be damaged. So I will have to run my analysis from this flood depths is 0 to flood depths of 3 or 5 meters to see how much I'm gonna save. And then I need to check something. If, like, for example, you will have a bladder dam around your building, but actually the water might back up from the ceiling because you have pipes out there and the water can goes in. And so if you don't have a non-return valve, so the water will come up from different sources. Will come from the toilet, will come from the bathtub, will come from everywhere. So is there a non-return valve? Are the water flood? Are the walls flood resistance? Is there a flood barrier? And what is the barrier height? Because the barrier height is very important. Okay, and then I run a fragility and damage analysis for every component and see if this component is gonna survive or not. So this is the component damage analysis. I go component by component and see if this component is gonna survive, the other component is gonna survive, and keep doing simulation for each component. And then do building damage and see how much the entire building is going to accumulate losses. So for example, let's assume that you were able to build a water barrier around your building that has 1 meter height. So your building will be surviving and the flood depth is less than 1 meter. But if it's more than 1 meter, so you are losing all the things that you saved, and the curve will go up from this point, not from 0. Because the water is not going to start from 0. The water is going to start from here. So all the components that are below this level is going to be damaged. So you will start to have this directly. Okay. And same thing with the fragility. You will have no damage until 1 meter, but once the flood depths exceed the 1 meter, you will start directly on damage state table, the damage state 3 and damage state 2. You are not starting from damage state 1. Okay. Also, what if we were able to implement water pumps? Water pumps helps to decrease the flood duration. Flood duration helps to, for some components, but actually there's components that are water sensitive. Once they hit with water, they will be damaged. But wood components, metal components, structural system, yeah, it can sustain some flood duration. Like it can be soaked in water for like 1 day or 2 days without any foundation problems or without any like damage problem or any structural damage. So components are different. So we were able also to capture the impact of flood duration. And that's actually what the multivariate fragility functions do. So since we captured the impact of flood duration, if I take a section in this surface at 24 hours, I will have this loss curve. But at 60 hours, I will have another loss curve that is much higher. And if I have like 150 hours, it will be much more. 10 days, it will be much more, right? So based on how much aeration reduction that the water pump is going to provide, I will pick which curve that can best my building, okay? So this is also what the fragilities can capture and what the multivariate loss function can capture. And also this is the fragility at each duration, like I have 5 fragility surfaces for each damage state, like damage state 0, 1, 2, 3, and 4. And I can take sections at each of flood duration. For example, if I have flood duration 1 day, I will not hit damage state 4 because my structural components can be soaked in water for like 1 day without any damage. Okay, but damage state 4 will show up if your building has 8 days flood duration. The foundation can have the water, and the foundation might like have some scour, and there's some settlement, so you will start to have some serious damage with flood duration exceeds 6, 8, or 10 days. So also this shows how can we capture, and since we developed the fragility function at the component level, so what if you were able to elevate some components, like the figure that I showed to you? This actually one of our results example that shows the blue curve if you didn't elevate the water sensitive components, and the red one if you elevate the water sensitive components. So can you guys see at some point elevating the water sensitive component doesn't help? Why? Because as I told you, if you elevate these components like 3 meters, so at 3 meters, if the water depth is more than 3 meters, it will be damaged. So you will not have any saving. So, but it can work if you have 1.4 meter flood depths, okay? But this is like less than 10% or maybe 12%, this amount of loss reduction, but it can help if you do it at the entire community level. And it's still some savings like $15,000 or $20,000 or something like that. Okay. And also, you can investigate a combination of flood risk mitigation. Like this one shows what if you were able to use a bump to decrease the flood duration from 10 days to 1 day, and in the same time, you have a flood barrier. So this one shows the flood barrier. If you have a flood barrier of 1 meter, so there is no losses, and this is the impact of duration, okay? So there are many things that component level fragility can help you to investigate. Okay, same thing with wind. If you are investigating wind and you can develop component level fragility for this connection or this shingle or this wall, so you can investigate the impact of mitigation. What if I increase the number of clips here? What if I increase the number of nails or change the material? You can do all of this. One other thing for mitigation is to investigate the impact of community level mitigation. What if you were able to, if I'm talking about flood, if you take the water and store the water in some place, and we call this retention system, to build a retention system somewhere that has inlet here and take the water from the river and take the water for some time, and when the water flow is getting down, you keep pushing the water out of this retention system. So it's kind of regulate the flow. Did you guys see the hydrograph from last time? The water flow is going up. So what you do is take an amount of water and reduce this water hydrograph until the peak is gone, and then you keep pushing the water back to the river. Okay, so this is one of the things. One of the things is like to protect the floodplain by building levees or dikes, something like this, or like floodgates at this location. So if you guys remember from last time, we had a spot that has the water gone into the community. If we were able to build a gate and regulate the water from this location, so we can block the water from getting into the community. So this is one solution. Actually, yeah, I have a simulation here that shows one of our solution for 1/10. Like we had the water, we did. So the thing is, we tried to build a gate here alone, and we found out that once we build the gate, the water keep accumulating behind the gate and the water coming from the other side, like from the left and right. So the water trying to find a way that is at lower point and hit the community. So what we did, we built the gate and we increased the levee elevations and the embankment elevations on the side. And this is actually how it worked. Like here you see it blocked the water and also blocked the water from getting inside here. But it also has some problems. So there's nothing is perfect. Like when we did this, some buildings here got flooded that were not flooded before, still got flooded, but lower number of buildings. We protected 28,000 of buildings, but we got like 50 buildings up there that got flooded. So we can buy out these buildings, we can elevate these buildings. So there are other solutions. So that's what I'm saying. One solution is not gonna solve everything. So we need to find alternatives and we can get them together to solve the entire problem. Okay. All right. So this is the, and yeah.
Yeah, I had a quick question. Is there like, I guess, like a way to, I guess, like validate the flood model? Maybe like
Yeah.
flow velocity?
That's what we did actually for Lumberton. We have been to Lumberton since 2016. We go like 2 times per year. And this is a part of longitudinal field study to validate not only the hazard, but also the damage. So we go collect water, high water marks, like we go at buildings and measure the water level and compare it with the hazard model. And also assess the damage, like we do interview with the household. How much losses do you have? How much claims insurance that you get? So we do damage, and actually we do visual damage from the outside of the building and see how much damage that they have. And we develop damage fragilities based on the damage that we see in the field, not the numerical models. And we keep comparing between them. Yeah.
And one more question. When you do the model for that community,
Yeah.
do you also model the other communities that can get affected if you put measures to avoid the water to come there?
Well, yeah,
Water
actually,
will find a way.
it is the same community. Like actually, yeah. So when you put something, it will affect, but
Yeah.
how? What is the extent of it?
Uh-huh.
So the extent was within the inside community. They didn't affect the other communities because this is a local thing within the community. So, but yeah, if there's adjacent community, it can affect them. It depends on what measures that we are using and what is the scale of these measures.
Okay.
Yeah. So I want to give like also a quick example. We have like how many? 20 minutes, right? Okay. And actually, that's actually everything. But I want to give you more examples that what I did is not only applicable for flooding, and you can do it for any other hazard: earthquakes, wind, tornadoes, hurricanes. So this is an example on multi-hazard hurricane risk analysis. So for flood, it was simple because it's only one hazard intensity, flood depths. But if we look at the hurricanes, hurricanes come with wind, with surge, with waves, with wind-borne debris, with wind rainfall intrusion, with water-driven debris, lots of hazards. But we can get distracted by all these hazards. We had to pick something to focus on. So we focused on the direct hazard, the surge, the wave, and the wind. So the difference between the surge and the waves. So let's assume that this is our building. Yeah, this one. And let's say that this building is at this level and we have the water here, okay? So the surge is that the water in the ocean get pushed from the ocean and get inside the community. So the water will be as high as this, okay? And the waves is on the top of the surge, like it will be something like this. Okay, so you have a surge and the waves on the top of the surge. Okay, so this is the difference between the surge. The surge is inundation, like flooding, but the waves is like very, very serious thing. It causes damage because it has momentum and it has velocity and it hit. So, so it's on the top of the surge. Okay, so we agreed that hurricanes have 3 main components: wind, surge, and waves. And we measure them. Wind, we measure it by wind speed. Surge, we measure it by surge height. Waves, we measure by what is called significant wave height, okay? Or let's say wave height. What is the wave height? Significant wave height is the maximum 1/3 of the maximum wave. So it's kind of like complex, but this is not the story here. The story here is what is the hazard intensity of these 3 main hazards: the wind speed, the surge height, the significant wave height. Okay, we developed a multi-hazard model that take all these hazard intensities, like what we did was flooding, we did it with hurricanes. We developed a hazard map for the surge, and a hazard map for the wave, and a hazard map for the surge duration or the inundation duration, if we include the duration in the hazard, because if the water is gonna still for a long time, it's gonna cause more damage. So we included the duration as well, and also the wind speed. But right now, it's getting more complicated. In flood, we overlay the flood depths with the community and identify what is the flood depths at each building. Right now, we need to overlay all these hazards with the communities and identify the hazard intensity for all at each building for all these hazards. We need to know for each building, what is the wind speed at this building? What is the surge height at this building? What is the wave height at this building? What is the flood duration at this building, right? We need to identify all 4 of these. And the thing is, right now, you will have a complex damage. You'll have some damage that comes from the wind, right? So what do you guys know? What is wind that affects more? Affects the foundation more, the walls, the roof. Roof is the most significant damage from the well because it's the one that more exposed. And also walls gets damaged, right? So foundation is less vulnerable to wind, right? So how about surge and wave? So does surge and wave, what is the components that surge and waves can affect? Mostly is the foundation because it's coming, the water coming from the ground, pushing the foundation and pushing also the walls, okay? But roofs, it depends on the wave and surge height. So each hazard has different characteristics, right? And causing damage. So that's why we developed separate fragility functions for each one of these hazards. Like we have a fragility function that can capture the components that are damaged by wind, and fragility function that can capture the combined impact of surge and wave. Right now, like a few minutes ago, I told you that there is what's called multivariate fragility. Same thing here. For surge and wave, you can have a multivariate fragility that can tell you how much damage that this building gonna have at a significant wave height of 3 meters and a surge height of 5 meters, right? So this is what this function do. And the other thing is we have also a flood fragility function that can tell you how much damage that you will have or your component is going to have at a specific flood depth and also specific flood duration. And then using these fragilities, we were able to know how much damage or total damage from surge, wave, and wind for your entire building. So for hazard modeling, we applied this approach for multiple communities and actually in the Gulf of Mexico and also in the Atlantic. So we applied this method for Waveland, Mississippi, and we used Hurricane Katrina in 2005. We did this for Galveston, Texas, after Hurricane Ike in 2008, and also Mexico Beach, Florida, after Hurricane Michael in 2018. So this approach has been applied for numerous communities, and also for the entire state of North Carolina after Hurricane Florence in 2018. So we applied this approach for many communities. And the hazard models, like actually it's a collaborative work because usually the coastal hazard is developed by coastal engineers. So coastal engineers can use what's called the AdCirc and SWAN models. These AdCirc develop surge hazard maps and SWAN models develop wave hazard maps. So by a coupled AdCirc and SWAN model, we can get surge and wave hazard maps. And also we were able to use a numerical model for the wind model using Pullen model. And we were able to get, for example, this is the state of North Carolina, and this is Hurricane Florence. This is the hazard maps, how it looks like. This is how the wind speed for the entire state, how was it? And actually, most of the wind speed, like this line, is 33 meters per second. So all this is exposed to wind speed less than 31 meters per second, which is like, if you have a fragility curve like this, and I'm telling you, this is the wind fragility, and this is a 31 meters per second, and this is 50 meters per second. So if you have a 31 meters per second on a community, how much damage you will have? It's a 0, right? So what we did, we isolated the building that are vulnerable to wind speed that doesn't cause damage. So this line is going to say that this part of North Carolina is going to have wind damage, but this part is not going to have wind damage because the wind speed didn't reach the threshold that can cause damage. Okay. But it's different with surge because surge has a limit because the water gets inside the community or gets inland, but doesn't reach here from the ocean, right? So this is the wave hazard map and this is the surge hazard map. We have all these maps in place. And then the second thing is to model the community. So we apply the same thing. We develop the archetypes and we have archetypes for flood different from archetypes for wind because if we are developing archetypes for flooding, so flooding is sensitive to the foundation type and the elevation of the building, but the wind is not sensitive to the foundation type. Whatever foundation type you will have, you will have the same pressure profile. But wind is sensitive to the roof shape. If you have a gable roof, it's different from the head roof, right? But flood doesn't matter. It's a gable roof or a head roof. So that's why it should be different archetypes. For wind is different from flooding. So we have different archetypes for wind and different archetypes for flooding. As you can see, this we have 15 archetypes here, we have 19 archetypes here, but this is not the case. Anyway, we need a model of the community. We need to identify what is the building type for each building in the community. Then we overlay the hazard map with the community. And now we don't have one hazard map, we have four. We have surge, we have wind, we have waves, we have duration, and then we identify the hazard intensity at each one of these buildings, okay? And this map shows the exposures of the building, like the building that was in the blue zone are exposed to wind. And the building that are in purple are exposed to surge, wave, and wind. Why? Because the waves is on the shoreline, right? The waves actually can jump up at the shoreline, but when you go inland, the waves get less, okay? So this zone has wave and also has surge and has wind. And as we goes inside, the wave impact get less. So you will have only surge, like the green, and some wind. And then when it goes inside, you only have wind, right? Because the wind can go inland as much far as it can go, right? Not as the water. But here, this part is the orange zone is exposed to surge and wave, but the yellow zone is exposed to surge only because the wave impact here was maximum. And as we goes in, the waves is less and we only have surge. But also we have wind at this location, but the wind speed is less than 31 meters per second. So we had to neglect it because it will make our analysis more complicated and it's not going to cause damage. So that's why we neglected the wind in this zone. So we are done with the exposure. So the next part is the vulnerability. So we use the fragilities that I showed you. We calculate component damage that coming from flood, like interior content and structural components. We didn't account content damage that comes from wind, because mostly wind is causing structural damage. It's caused damage to the roof, it's caused damage to the walls, but most of the content damage comes from water, when the water breach inside the building from flooding. So we use the fragility curves that we developed for flood to account for component damage. And the input for this fragility is the wave and surge, like surge and wave, not wind, okay? And then this wind hazard maps, we used it as an input for the wind fragility to account for wind damage. And the surge wave is structural damage, we calculate from the wave and the wind. Okay, let me tell you, the content damage, let's separate the building into content and structural, okay? So the content damage, what the source what the hazard source that can cause content damage? I don't think that wind can cause content damage unless the wind triggers other hazard. Like you have a hole in your home and the wind triggers wind rainfall intrusion. Now you will have content damage, right? So wind will cause purely structural damage to the walls, to the frames, to the shingles, to all these components. So it causes structural damage. So, and then we divided the water into two damages. Water can cause content damage and structural damage, right? Okay, so the surge, when it combines with the wave, because if you have a surge height that low, so the waves will be that low. But if you have surge height up there, because the waves is always on the top of the surge. So you will have to combine, when you calculate structural damage, you will have to combine surge and waves. You cannot mix the waves alone, okay? So we developed a surge wave fragility function, where is it? Yeah, this one. That can only calculate the structural damage, damage to the walls, damage to the frames, damage to the foundation. And then we have other fragility functions that only capture the content damage that comes from the water, which component is wet and how much damage that we have if this component got wet, which is this function. So content damage is calculated from fragilities separate from other fragilities that calculate the structural damage. And then once we calculate both, we sum them together and we get the total building losses. So, and this is also the damages state is not important at this point. And this is how we calculate the losses. Like right now, you have a wind fragility that tells you what is the wind damage state for your building, and a surge wave fragility that tells you what is the surge wave structural damage state for your building, and flood fragility that tells you what is the content damage state for your building. So you have three, and you get what is the maximum of them, and you assign it to your building. Like for example, if the wind, if a hurricane comes with a very low speed wind, but has a high surge and wave hazard. So the wind caused damage state 1, slight damage to your roof, but you have damage state 3 to your content and your building. So what damage state you will have? Damage state 3, because it's already, my content is already damaged and I can't live in my home. It doesn't matter if the roof is like have damage state 1 or 2, right? But let's assume that a hurricane like Hurricane Michael comes with very high wind speed that can cause a very high structural damage, but comes with like amount of water that is very low and cause like damage state 1 to your content, but your building are without roof. Can you live in your building? So the wind is going to be controlling your damage state. So that's actually what this equation is doing. It tells you what is the dominant damage state for your building. And then this equation tells you it converts from probability and multiply probability by replacement cost and tells us what is the cost of damage that comes from the surge and wave, the wind, and the flood. Okay, so it's kind of complex. I'm not going to explain them, but this is how it works. We calculate them separately and then we sum all them up. And this is at the component level. And also when we move to community level, we need to develop new algorithm that can go building by building and do the same thing for each building. And that's actually what this algorithm do. So this algorithm actually, it's account for the hazard. So it starts and at each building, I need to know what is the wave height, what is the surge height, what is the wind speed, what is the flood duration. And for each building, I need to know this information, the location, the foundation type, the first floor elevation, the ground elevation, so that I know how vulnerable is this building. Because if this building is at that high, it will be less vulnerable. And if that high, it will be less vulnerable. So more vulnerable. So less vulnerable, more vulnerable. And I need to read all the fragility functions that I have, and I do building by building, and I run all my damage analysis. And once I finalize it, I go to the other building, and I keep looping and do the same thing for each building. Okay. And once I'm done, I will have also a visualization that shows me how much damage that each building is going to have, and I can sort them based on flood damage, because I have flood fragility, wind damage, surge wave damage, and also total damage. Yeah, so I'm not sure if I have, yeah, here's the total damage for each building. That combines all these damages together. And I can have this damage in terms of content loss or also structural loss because I have them separated, right? So I can know how much content loss that each building can have, how much structural loss that each building can have, and how much total loss that each building is going to have. So this was an example. Yeah, so let's see how much we have. We have like 4 minutes. Yeah. Okay, so for community resilience analysis, let me wrap it very quick because this is very important concept. I will have like maybe one lecture at the end. I'm not sure. I don't think that we are going to do something with community resilience. We will stop at the vulnerability, how we quantify vulnerability. But it's very important that you know this concept and how this concept is working. So right now we only cared about the building's damage, right? But I told you last lecture that building's damage is not the sole component that controls the functionality of the building. Maybe your building is not damaged, but it doesn't have water, it doesn't have power, and you cannot live in your building. So right now, the standards are trying to move from the concept of damage or the concept of failure to the concept of functionality. Is your building is functional or not? So, and this depends on 3 components: the household itself, the buildings, the networks. Like buildings, we are talking about the physical functionality of the building itself. It has everything that makes it functional. The walls are not damaged, the door is not damaged, the structure is safe. Networks, we are talking about your accessibility to water, to power, to gas, to service, like Wi-Fi service. Some of them are very important to life, some of them are less important. Like you can live without phone for like 2 or 3 days. I'm not sure, maybe some people can live without phone for a month, okay? But you cannot live for a long time without power and water, right? You will die, right? So you need power and water. Maybe the water is much more important. So you need lots of utilities. You need sewer, you need gas, you need telecommunications. So all this are in network. Household needs, like your needs to healthcare service, your needs to educational services, your needs to food, shopping, gas stations. All this is also controls your resilience, your functionality. So this is an example of how interdependent all these relationships. Like you have a power network, and this power network feeds a water network and also feed the transportation networks, the signals, everything. So you have your community, for example, and actually this can be as big as like 10 layers. We can add another layer for the telecommunication, another layer for gas, another layer for power. So the community has many of these layers, has a power network that feeds the water network, feeds some pumps that can pump the water to your place, and feeds the water treatment plant that can clean the water, and also feed the transportation network and feeds many other networks. So when the power is down, many things can be down. Water can be down, telecommunication can be down. So this is interdependent by itself. And also cross the build, like the buildings, like our building is cross-dependent with these. Like you need power, you need water, you need transportation, all these feeds the buildings. And if we think about buildings, we can segregate them to residential sector, commercial sector, social sector. So residential is the residential building, commercial is like the retail, the shopping centers, the gas stations, social institutions like hospitals, schools, many like community centers. And you can add many other layers. You can add service sector like the police stations, the fire stations, all these things. You can add the recreational sectors like the clubs, the gyms. You can add many of these networks. And you have people, like you have household, and this households, there's embedded like people that work, like they are labor in businesses, they are employees, they are staff, and they have kids. These kids are students, are patients in hospitals. They are like, so you have lots of layers. And all of this is an interdependent problem. We need to solve this problem because this building functionality depends on these networks and depends on this building itself and depends on the accessibility of this household to all these services, right? Okay, so actually this shows how complex it is. So for example, and this is actually shows how we try to approach this problem, how we try to model a community. So this is a part of a community. And to do this, we need to identify what is the size of the household of each building, and what is their race, what is this ethnicity, what is their income, what is their number, like how many kids do they have, how many people live in this household, right? At each housing unit. And once we do this for housing unit, we will know for the entire building. So we did this, actually the census data provide us with how many people live in a census block. Like this is called a census block. And it tells you there's like 10 people or 12 people live in this census block, but they don't tell you how many people live in each building or each housing unit because this is confidential information. So we have a social scientist that developed an algorithm that can allocate these people to each one of these buildings and tell you how many people live in each one of these buildings. And we call this allocation algorithm. And same thing, you can allocate these people as a staff in a hospital or as a staff in a school or as labor in the market. So you can have labor allocation algorithms, staff allocation algorithms. You can know customers allocation. You can allocate them, you know, where they shop, where they go to gas stations. You can know all this information with allocation algorithms. Same thing with a network. If you have a network and you know the topology of the water network or the power network or the transportation network, you can know the service area of each network. And if a line in this network, like if this line is down of a power, you know that all this neighborhood is not going to have power. So we were able to link all of these. Like this is an example that shows a school here, and this is where the kids that goes through this school. And same thing, the staff that work in this school. We have a school here. This shows where the people live with respect to the school location. So this is an example of the allocation. And this is the household. Like here, there's lots of people live here. Less people live here. Like the most of blue is this is a heat map that shows where is the darkest spot, which most of people live. And there's lots of information, but this is actually what I want to say is like, this is very important when we think about community resilience. We need to think about every component. The buildings, the networks, the households, all these information is very important. And not only structural damage is the sole component that can tell you if this building is functional or not. So I hope that give you some overview, and engineers themselves cannot do this alone. So we need other people to work with us, like social scientists, economists, urban planners, So this work hasn't, it wasn't only me, it's a big group of like 30 people across the country. Some of them are social scientists, some of them are economists, some of them are urban planners. We work together to come to a solution. And so it's not only a problem that we can solve alone. And I hope that I trigger some idea that you can think about. And starting from next lecture, we will start the main core of the course. Like we will start with the probability and everything. So you guys be ready for some good stuff. Okay, sounds good. See you guys.
Maybe it's just a short question.
Yeah.
I was looking at the loss model that we have there, and I was looking at comparison with, I think I saw one with hurricane loss. So I was going to ask what the difference is and like, what else is like the hurricane loss. So hurricane loss model, I think it was on slide 34.
Okay, because the slide
I
numbers.
don't even know what the difference, what we have there and those other hurricane.